Okay, so hello everyone. So welcome to attend our this week Ruggers in Efficient AI seminar. And today we're very glad to have the Professor Cunxi from the University of Maryland to give us this talk about the optical neural network. And Professor Yu is currently assistant professor at the University of Maryland College Park, and his research interests are pretty broad and have the novel algorithm system hardware designs for computing and security. So before joining the Maryland, he was assistant professor in the University of Utah and the postdoc at Cornell. And his work has received the Best Paper Award at DAC, Best Paper nomination at ASP DAC, and the IEEE Transaction CAD, and also NSF Career Award, and the American Physics Society DIS Post Award. And Professor Yu received his PhD from the University of the Massachusetts Amherst in 2017. So now let's welcome Professor Yu to give us this talk. Cunxi, it's your turn.
Yeah, thanks for the kind of introduction, and thanks for having me here. Today I'm going to talk kind of a branch that I explored at the beginning of my tenure track position. So I usually work on computer engineering, mostly focus on EDA, algorithms, logic synthesis, formal verification. So it's very different, but I want to show how we view optic neural networks or optic systems as a computer engineer. So that's why I call it a computer engineering journey to optical neural networks. So we talk about infrastructures, core design algorithms, and also how we model the entire system from physics all the way to the entire application level. So this thanks for all the sponsors, and as Bo just said, I started this project at the University of Utah, and I have moved to University of Maryland recently. So I guess it's I don't need to introduce quite a lot in why we are exploring new hardware systems for AI applications, and just showing the trend that there are so many different design styles that try to optimize the efficiency of AI inferences. Yeah, we're talking about inferences only in this case. But as you can see in this figure, right? So there's obvious trade-offs that you can either get a really high throughput, but at the same time you're going to sacrifice on power consumption. On the other end, if you really care about low power as your main target, you're going to lose the peak throughput of the entire system. And this figure is a little bit outdated because, as you might already know, yesterday or this morning there's big news from Grok. They can do much faster large language model inferences, which is there are a lot of new design has been released. But what I want to really point out is this trade-off curves, right? As you can see, it is always bounded by this kind of trade-off curves, which is limited to the digital technologies these days. So what we want to explore as from the optic point of view is, can we really break this frontier to move the efficiency all the way to the left top corner? That is, at the same time, we're offering extremely high throughput, but also give you relatively low power consumption. But there are a lot of challenges. I think this is the challenges I summarized, not just only for, not just valid for optical system, but in general for a lot of emerging technologies, right? So if you think about optical AI system, right, it's two-part, right? Optic and AI. So obviously you're going to need domain knowledge of both of these two domains. Like, you need to understand what is machine learning algorithms, how does neural network works, how does the backpropagation and training algorithm works in training neural network models, right? So, but since we are moving everything from digital neural networks to optical neural networks, you also, of course, need the fundamental knowledge of how do we model optical process. And specific in this figure is showing the key kernels of our system is called diffractive optical neural network. This is showing the diffractions. I'm going to break down the details in the later slides. But at the same time, you're going to need more, right? So for example, when you start modeling the entire physics phenomenon of these diffraction of optics, you're going to need a lot more computation consumptions, right? So if you really want to make a training of large-scale diffractive neural networks or optical neural networks efficiently, you're going to need some knowledge or skills of high-performance computing, right? So, for example, if you really want to make this large scale and more runtime efficient, you need to use CUDA programming to accelerate the entire kernels, right? So, at the end, we really want to deploy these things to a hardware, right? So we really want to see whether this thing is going to work, because it's a big question that we ask for all the emerging technologies, right? So, but when we start deploying to our own systems, so this is one of the systems we worked on, we start realizing there is a huge amount of miscorrelation, since you can't really build a one-to-one exact correspondent numerical model to the actual physics, right? So here we identify the big challenges of core design. You really need to correlate from the software, which is the modeling, the training algorithm, all the way to your specific hardware specs. So our work is basically targeting to address how can we develop an optical AI system more effectively without knowing every single piece of these four knowledges. Okay. But in addition to just domain knowledge, I also want to identify that there's a big lack of infrastructure support for emerging technology, especially in optics. So I just want to give an example, right? If you work on digital design, right? So you, such as IPGA or ASIC design, you know where to start. You know what language you're going to use, right? So you start with HRSC if you want to do Xilinx HRS compilation all the way to FPGA, or you can start writing a Verilog that will compile all the way to the GDS2, either using open source or closed commercial solutions such as Cadence Genus, right? So, I mean, if you're thinking about neural network development, like the traditional, the conventional neural networks, it's even simpler, right? So you have PyTorch or TensorFlow that prepare almost everything from data preparation, neural network construction, even runtime optimizations with frameworks such as TVM, and all the way you can deploy and train your neural network efficiently. However, there's a big gap here because we don't have such a framework, right? So that's why we also thought about, can we build an open source infrastructure that will simplify everything from the programming phase. And the last thing I want to really emphasize once again, this is one of the examples we want to show you at this stage is, on the left-hand side is the numerical simulation we got with our physics modeling, and on the right-hand side is what we actually measure from the system, right? So there's a big gap just from the physics to system modeling, and we want to address that from the co-design point of view. So that kind of, in order to target to address these three challenges, right, we kind of break down into three pieces, right? So programming infrastructure, and domain-specific algorithms, and end-to-end core design with a real-world case studies that will be shown later in this talk. So so I want to start with this first, because assume that we have a good knowledge of machine learning, because it's all over the place now. I want to start with discussing like how do we model optics and how make this entire thing trainable in our infrastructure, right? So the key is to, if you want to use efficient training algorithm or backpropagation mechanisms that has already been well developed in convolutional neural networks, the only step you need to do, I shouldn't say only because it's not that trivial, is to make the entire physics phenomenon differentiable, right? So we're going to talk about differentiable physics at the beginning of our infrastructure development by quickly introducing what is diffractive neural networks, okay? So this is it looks very similar to a conventional neural network, right? So you have layer by layer stacked with the input on the most left-hand side and reading the result at the final output on the right-hand side in this figure. Okay, so each of these layers is called a diffractive layer, and that includes phase parameters that is going to kind of as the performs as the neural network weights. So let me quickly discuss the differences, and then we break down the details in the next slide. Okay, so instead of having digital numbers that are representing the images like real numbers, for grid scale you have negative 255 to 0 to 255. But here we encode everything with light. So all the input is encoded with light. So it's a complex value instead of real in numerical simulation, but in real world it's just a light. And instead of doing like operators such as convolution, dense, and pooling, the only two operations we do here is called light diffraction and phase modulation. So I will show you how that works. The key difference is that the entire computation of this neural network does not consume any digital computing, right? So it's pure light propagations. If you just look at the computation part, which is the 3 layers, so the computation consumes 0 energy in this model, okay? But that doesn't mean that our system doesn't consume any power. Otherwise, it's going to be 0 power. 0 energy neural network, right? It's almost impossible. So because you still need light source, and you need to read out the result using detectors, right? So so let me break this down, right? So the first step is called phase diffraction, right? So we need to model everything in differentiable format, as I said. If you don't understand any of this, it's completely fine. So the phase space diffraction can be basically modeled using these Fourier and inverse Fourier transformation that is encoded here. As you can see, all these operators are differentiable. If you understand what is free space diffraction, you can see this is basically Fresnel approximation of light diffraction. But just keep this in mind, everything can be encoded as a closed and differentiable format. And we can keep that going to the next stage, which is called phase modulation. So this is where we're going to introduce our trainable parameter. As you can see, we take the output of the light diffraction, which is our differentiable computations, and if we add a complex matrix multiplication, and the phase modulation performs in this way. Okay, so if you understand how phase modulation works, you will see how this works. But if you don't understand that at all, it doesn't really matter. All you need to remember is that the diff mod operator is a fully differentiable mapping of the entire physical phenomenon. Okay, and this in the second stage of phase modulation is where we introduce the trainable weights, which is every single pixels that shows here. Okay. And once we have an abstract model of this, so we discuss the mass of every diff model, and this entire model can be just represented using a conventional expression such as neural networks, right? So you have layer by layer, and the input keep propagate into the next layer. And at the end, we're going to read out the output, right? So in this case, we define theta 0 to theta 2 as the trainable parameters in this case, which is n by n defined by the number of pixels in each of the diffraction phase. So at the end, how we're going to read out the output, right? So because light is when light propagate, right? So the intensity or the energy of the light will change since you give different parameters here, which is our trainable parameter. And what we are going to do is measure the final energy at the output or intensity. So the way we calculate that is basically putting a squared plus b squared, and we calculate the intensity, which is what we measured at the detector phase. Saying for this simple example for a minutes classification, we're going to pick the highest energy index as the classification label, which is very similar to using cross entropy or argmax to do traditional neural networks. Okay, I hope this is clear. And so the reason why I want to review this quickly is that I want to show you what components are really needed for building an infrastructure to support the design and optimization of this type of neural networks, right? So you need to have modules that define your input, like how to define different type of laser profiles, how to do different type of input encoding, because even though you encode with intensity, you don't have the capability to represent arbitrary intensity value for some devices. And you need to form, just like key operators, like in PyTorch, you encode everything in NN module. So we need to implement our own operators and make them differentiable, right? So at the end, we're going to implement the modules that for reading out the output and that matches the detector profile. So that's why we form up this very simple intermediate representations that we include physical kernels, a neural network container, just like you can manipulate the layout or topologies of neural networks, just like PyTorch. And at the end, we're going to deploy the training modules. So the reason why we want to make everything differentiable is that we want to maximize the uses of existing backpropagation mechanisms, since they're already very, very effective. So at the end, we discuss some of our optimizations for runtime and the fidelity, which is will be discussed in the code design phase. So this is the overview of the system. So if you recall the slides that I was showing, like how digital compilation works, right? So we start with high-level synthesis, state code, if you want to work on PGA, and then there goes logic synthesis, physical design, and all the way to deployment, right? So I look at this entire design process just like how we do in EDA research, right? So we start with a very high-level description, and we have a bunch of modules that define how the diffractive layer works, and then we do the training, and we do the hardware deployment, just like how we do in EDA or in convolutional neural networks. The reason we want to do this is to really minimize the gaps when people want to, let's say, explore a little bit about optical neural networks, but they come from background complete from digital. Okay, so and if you see how this works out, it's very similar to how you use a PyTorch to build a, let's say, minist CNN, right? So so the design flow is going to be like this, right? So initialize the entire thing. So here, the first step is going to initialize the data set, right? So you need to initialize your data loader. Remember, here we represent everything in light instead of digits. So you need to convert all the digital format images into a complex domain, right? So we have that already supported. So at the same time, you also need to initialize your laser profile, right? So you need input defined because laser might have different profiles, different wavelengths, different power. And at the same time, we will start constructing our optical neural network modules. You can see it's very, very similar to how PyTorch works. We just stack things together in a sequential container. At the end, once the model is all constructed, remember everything is differentiable, so we can just use, we basically part in the backpropagation mechanisms, and you can use whatever optimizers that is supported by PyTorch or TensorFlow in this case. Okay, so we also we also implemented GPU acceleration for our specific operators here, similarly as PyTorch syntax. So you can deploy to either single GPU or multi GPUs, right? So we also we're going to discuss about how design space exploration can be done in this system. At the end, so once the model is trained, right, just like what we got from a CNN or a dense like MLP, so you will have all the parameters, right? Unfortunately, here we can't just directly deploy these parameters to a hardware because there is the different mappings to that, right? So we have so in order to minimize these gaps from the knowledge to optical neural networks, we also make a very simple mechanisms that will support arbitrary device mapping if you're just curious about how optical neural network works, or if you're like a device person and you want to evaluate how good is your device for optical neural networks performance point of view, and you can also use our system to do that. So that will be discussed. So this part is covered by the second part of the talk, is the core design algorithms. So I want to just show you a few more details about this, the most important, which is the kernel. And the thing I want to point out is there's a lot of things, but you don't need to care. But there are a different type of approximations we implemented here, so to support a diverse range of diffraction setups. Okay, so we have Fraunhofer, Sommerfeld, and we'll also include FDTD verification to so which is much slower but much more accurate to do some verification in this system. So let's see how this system will encode a specific hardware that we have come up with. So this is a visible range optical setups, right? So we have input images encoded on the left-hand side. This is a green laser at 532 nanometer set up in our lab. And we have built 3 diffract layers. Okay, so we want to have a model with 3 layers. We want to kind of proof of concept, right? So, and then at the end, we use a camera or detector to read out the intensity of the light at the very end, right? So we want to see how our programming or infrastructure that can show you a one-to-one correspondence encoding of this hardware, right? So if you saying you have a different hardwares, you can just follow the same steps and make it to your own. Okay. All right. So the first thing is define, okay, the diffracted layers, right? As I said, laser I already defined is just a single line in our infrastructure. Here you need to have all the parameters that encoded, right? So for example, in the layer, you're going to define, okay, what is wavelength? So wavelength is going to be the exact wavelength of your laser, because the entire the wavelength doesn't change, right, during the propagation. And the pixel size defines, remember, in this realization of the optical system, right? So we have each of these is called diffraction pixel. This is the dimension of every single pixels, right? So this is a 36 micron, which is defined by whatever device you bought, right? So this is what we got from hollow eye called spatial light modulators, and that is 36 micron. The resolution is how large is each of these. So how many pixels you have at each of these diffraction layers, right? So 100 means 100 by 100. You have a square, which 10,000 pixels. So 10,000 trainable parameters per layer, basically. Okay, and the distance is 11 inches. Which is in between input image to diffract layer, or between the diffract layer, or between the diffract layer to the camera, right? So we use a unit distance to do that, but you can configure differently if you want, but we just, for simplicity, we just put everything into 11 inches. So the reason why I see a weird number here, because the optical table is engineered in US and is using inches, right? So that's why it's not it's a weird number there. We'll talk about amplifactors in our co-design algorithms, and you can name these just like convolutional neural networks. And then you have all of these stacked, right? So as you can see, I only have 3 layers, but why I have a 4th layer? Because when the light comes out from the final diffract layer, right? So the light will keep diffract before you reach the camera. And so that's why we, in the diffract layer module, we also implement a phase modulation off model. That means the light will just do diffraction without doing any phase modulation, because you don't have a modulator anymore. And once we construct this, remember, this is going to be just in a container, right? So a sequential container. You can just build the entire forward function, just like what you do for a convolutional neural network, right? So you do the forward function by looping through all the layers, and you just keep doing that. At the end, you're going to have a detector without the output, okay? So now this is the construction of the entire neural network, right? So what do we do in regular convolution in like CNN construction? So the next step, if you have a forward function, you're going to build up your training, right? So the training is very simple, since because we already done most of the work in constructing our kernels, right? So it's a fully tensorized and differentiable physics kernels, and it automatically support any type of autograd mechanisms from either PyTorch or TensorFlow, or even other deep learning frameworks. Okay, so and I just wanted to quickly discuss about the loss function, because the rest is going to be the same, since everything is differentiable, right? So it's very, very similar to how we works as a convolutional neural network, actually. So if you capture all the intensity of the targeted 10 areas defined here, since we work on 10 classes, right? So if you work on 20 classes, you're going to define 20 different regions here. And we're going to measure every single cells and put the average intensity or energy of this region, okay? And we will use that as a single number, just like what we do for a convolutional neural network output. We have 10 by 1 dimension vector, right? And then we're going to use just a cross attribute, whatever loss that you want to use for either classification or maybe something else, right? So if you want to explore different tasks. We were going to show how we model for segmentation task later on. But as you can see, the rest is going to be very simple. Since you take energy out, you normalize the energy, and then you can just treat that as a convolutional neural network training problem, okay? So the loss is going to be just the same as you build a MNIST classifier in CNN, okay? All right, so now let's see how this thing works out, right? So we have the model, we have everything trainable, we train everything with the algorithms, and we have a hardware, right? And the obvious next step is to deploy these weights to this hardware that is showing on the top. This is in the library system. We also show you develop a propagation realization mechanism, so we can understand how the light is moving around, right, in the system, right? So you can see the one is getting when diffraction happens, right? So it's going to be expand it a little bit, and then I shouldn't just say expand because they have, it's more complex than just expanding that, right? So, and you can see the energy is slowly move, okay, into the targeted region, right? So if I'm doing a classification for 1, I'm expecting the region of 1 has the highest intensity at the end, right? And you can see how this light goes out, goes to that region by propagating through the system. Okay, but the reality is it's always like this, right? So if you work on experimental mental works in optics, you can see there's no correlation at all, right? So it's completely noise mask at the end. So we want to understand what happened. All right, so this is we start identifying a few very interesting issues. It's new to me, but it's actually very, very normal in doing experimental works for optics, right? So if you look at this, this is the characterization figures for 4 different diffract layers specialized modulators we use, right? So first one is used for encoding the images, and 3 for encoding the layers. So if you don't understand anything about the coefficient or the spline voltage or the phase values, that is okay. But obviously, thing you can see, I just let you know, guys. Let you guys know, we bought these 4 layers of modules at the same time from the same company, or shipped to the department at the same day. Okay, and you can see they obviously behave very differently. Okay, so the first thing we identify is there's a coupled amplitude and phase response. So in optical system, right? So the amplitude and phase in our model is assumed to be decoupled, right? So they can be anything during the training. But in reality, in some of the kind of cheap specialized modulators like what we have bought, you don't have a decoupled encoding or a phase-only model. Okay, so that's the first thing. You can see there are 2 parameters that are changing differently. Okay. The second thing is what I said, right? So we bought everything at the same time from the same company, but they behave very differently if you compare SM1 with the second. So this one and this one. Okay. So how do we address this? It's beyond this issue because we might want to try this entire system on different setup, right? So this is we use a 3D printing method to build a terahertz optical system, in which case the thickness of each of the pixels, as you can see, right, they're different. They're kind of raw surface. So different thickness represent different phase or different trainable parameter values. Okay, and I can't just build a deployment backend for every single devices, right? And people might want to use very different stuff for their own optical setup, right? So how do we overcome these generalizability issues? Okay, so that's why we have thinking about can we do a very device-specific core design on top of our fully differentiable diffractive neural network modeling? Okay, so let's get into the algorithm side. So so I want to break down this into a very small scale representation so we can understand this problem more clearly. So if you look at just one single pixels in the phase modulation, remember phase modulation is the only place that the parameter is going the trainable parameter is going to change the functionality of the propagation, right? So this is the trainable parameter. Okay, so that's why we look at this only. This is the original encoding, right? So assume this is a phase-only modulation. You're going to get a coefficient 1 here, and this is the imaginary part, since this is a complex domain operation. So as you can see, in this case, there's a coupled responses between amplitude and the phase parameters. These 2 are correlated. Okay. If your amplitude is not a steady 1 or something else, it's not a constant, the values is going to change simultaneously, right? So for example, if your trainable parameter says my phase value is supposed to be 0.3 pi, okay? And you assume that A equal to 1 in the original model, which is not in this case, right? It's going to be 0.9, right? So your model and actual physics or actual hardware implementations is going to be different. Okay, so this is the first step of losing fidelity of our model. The second thing is that, remember, I can use arbitrary devices, right? So I might not use this brand of SLM in this visible range setups, I might not use a specialized modulator at all in a different setup like optical system, right? So using 3D printing, for example, I can't just do all these like mappings one by one for every type of devices. So we want to model this core design training to see whether we can handle arbitrary scenarios of either coupled responses or complete different scenarios of a device setup. Okay, so let's break down this into more details, right? So instead of having a coupled relationship, we want to encode every single discrete values from arbitrary devices. So for example, if I'm given a device with this kind of amplitude and phase responses, right? So you have basically two set of vectors that are changing simultaneously, right? So what it is doing is basically, if I'm selecting P1, so phase value from this phase vector, and at the same time I'm selecting for A1 from the amplitude factor. Remember, this is the coefficient for the cosine, and this is on the imaginary side for the coefficient, which is from the A1, right? So this is done by using a one-hot parameter, one-hot vector, and use a matrix multiplication that you can select, right? So the specific row here. But this thing is non-differentiable, right? So once you, if you work on neural networks, you probably know, for example, if you use argmax in your neural networks, and the argmax itself is not differentiable, right? So how do we address this, right? So thanks to Gumbel softmax or Gumbel tricks. So this is I'm not going to get into the details of this, but this is the algorithm that or mechanics that you can use to differentiate your one-hot vectors. So on top of these one-hot vectors, right? So we refined the formulation using Gumbel softmax by introducing a new set of trainable parameters that is going to be in float, and that goes through a Gumbel softmax. And we used so you can use either hard or soft. In this case, we use hard that we directly generate a one-hot encoding. But remember, this one-hot encoding is now going to be trainable all the way to the second set of floating parameters, which is the new weight. So instead of directly training, what parameter I should give in optical scenario, because it is not continuous in reality, right? So it's discrete. So we use this model to encode arbitrary set of values for devices, right? So either you use different brand of SLM, different like what we have, different SLM have very different responses to different vectors, right? It doesn't really matter. All you need to do is give me a list of values, okay, correspond to your responses, right? And it can also be complete different devices like the 3D printing. So how do you change that? So you're going to just say, 0, 1, 2, 3. So you're going to have, let's say, 8 of the values, right? It's a 1 is going to be thickness of 1 millimeter, right? Second is going to be second millimeter, right? So when we do 3D printing. So at the end, this algorithm or this modeling is giving you the capability to just do completely ignore how training, how do you quantize the phase and the amplitude values from a given device. So all you need to do is give me a list of values that you have measured on your own device or from the factory. Okay, so during the training of this system, we identify an issue, right? So if you look at this the system diffraction itself, if you understand how diffraction works, diffraction is majorly impacted by the phase values. That is, we also discussed that if you don't understand diffraction, it doesn't matter, because remember, phase is the parameter that is changing the functionality of your propagation, right? Amplitude is changing how you can see that the weight of each of the pixel in terms of intensity. So we want to introduce this regularization factor that to kind of balance the gradients go through either to the amplitude side more or on the phase side more, right? So and you can see in our experimental evaluation, right? So putting a slightly bigger impact regularization factor on this side is going to have a better performance because you kind of bias more gradient on the phase side instead of the amplitude side. Okay, but it's a new kind of a new hyperparameter because you can see if you give a bigger number, sometimes it's just going down, right? So the accurate, this is that training accuracy according to the epochs. Okay, And another thing you need to tune in this algorithm is there's a temperature. You need to give a temperature schedule if you want to use Gumbo softmax more effectively. Okay, so we discussed how that works in our ICCAP paper. So I will just give the details here. And I mean, some of you might think, oh, this is there's a obvious fit by using quantization aware training, right, or post-training quantization of this system. So we have compared all of these, but this is the result that is showing for the comparisons. So the main reason why the existing quantization method that did not work very effectively is they cannot directly consider the period problem of this phase parameter. It's saying 0 to 2 pi is same as 2 pi to 4 pi, right? So which is fully encoded by encoding all the discrete values in this case. But the more important advantage of this system using this algorithm is that you don't need to understand anything of how this training works, right? So as a user of this system or the algorithm, especially from the optic device point of view, all you need to give to this system is marrying all the responses from your device, right? So and then you can make a list, just like a CSV, make 2 rows of the responses, amplitude and phase, and they can put into the system. So this is kind of one of the big reasons why we want to explore this algorithm is that since we want to build a open source infrastructure, right, we want to make sure the usability is good, and this is what I think as the most effective way of doing arbitrary device encoding and arbitrary design scenarios. Okay, so after addressing this, we want to see, oh, does this actually correlate to the nature of the physics, right? So this was remember I have this figure that's showing layer by layer from input to output encoding, and this is another way, another angle of looking at the system. So as you can see, there is a black box around, and when the system operates, we actually have to close everything because remember the detection part is very sensitive to the energy or intensity. So if you have like if you open the box, that you're going to have intensity impact the system from the natural light, right, or the environment. So it's, as a proof of concept, right? So we basically using a black box that just hide everything, and we project everything to the detector region. So the simulation is showing in this video. You can see how the intensity that is shrinked slowly layer by layer into the region that you have developed. Remember, in this minist design, we have 0, 1, 2 on the top, and then you have 4 in the row, and then you have 3, right? So 3, 4, 3. So 0 is in the center of the bottom, okay, and 4 is in the middle, and 1 we already see that 0 is the very first in the first row. And this was the zip code when we worked on this problem, so that's why we picked these numbers. And the entire training is done within 10 minutes on 3090, and now it's even faster if you use a newer version of GPU. We just tested with 4090 Ti and that is about 4 to 5 minutes, right? So A6000 is around 4 to 5 minutes as well. And we got like 98 accuracy in the experimental evaluation. So the 98% accuracy is measured using the experimental, like which is actually detected on the optical devices, okay, the detectors. And the most exciting thing is that our entire infrastructure and algorithm that give you a one-to-one, not one-to-one correspond, but very close high fidelity correlations to the actual hardware we have tested. Okay, so of course, since the entire system now works just like how PyTorch works, but you have different backends, you can try different data set. Here is another examples that we tested on eMinist to do classifications on the letters. But as you can see, we have pretty big accuracy drop, and especially if you compare these numbers to convolutional neural networks like CNN. Still, we are working on very small scale at this time, and it's not getting really high accuracies at this moment. But if we increase the complexity of neural networks, we are able to get this a little bit higher. Okay, but what is the most important thing, as I claimed at the very beginning of the presentation, is about energy efficiency, right? So we have done a pretty detailed comparisons and in terms of energy efficiency. We measure everything as a bulky system, right? And we consume the entire system energies in doing inferences. So what we do is we use a rack power measurement of the entire whatever system that you use. For example, either edge TPU setups or GPU or CPU. We basically connect to that system. Either in idle we measure one power, and when we run something, and we will get a new power, and then we do the subtractions. For the optical system, is the same. So we plug in everything to the same cable, and we measure the dynamic power of it when we start doing inferences, right? So this is a actual measurement that got from this system. Okay, so it's about like 2 orders to GPU, CPU, and 1 order or 2 orders to edge devices, right? But remember, this system is still at very, very early stage, right? So it's not very efficient in the sense that it's not integrated, and also very bulky. So we're currently working on an integrated version of these. We're trying to put everything on a single chip. This is going to give you another order or 2 in terms of power efficiency. Okay, but this is just for the proof of concept. I think it's already very, very encouraging. So I also want to take the time to quickly show you how generalizable is our infrastructures. This is a completely different setup, but using exactly the same concept with doing diffractions, but it's in terahertz domain, right? So this is a 0.3T laser, and this is kind of on the lower end of terahertz laser, but I mean, this is the cheapest that we can get. So instead of using the specialized modulator, right? So terahertz, you can use these 3D printed polymer materials that to manipulate the trainable parameters, which is the phase values, right? So the set is the thickness kind of defines the phase values, like 0.5 pi or 1 pi. It really depends on how thick is your pixels here. And this is the 3D printer we got also very cheap. We got from Amazon like $400, and each of the ranges for the material is $5 for a bottle. So we can print this very, very efficiently. And how the system works is we do integrated printing that we have, for example, first layer and second layer that kind of connected using the side wall. And so we don't have the problem to do alignment in this case. But you can see this is fully done by our light-rich infrastructure. All we need to do is change the list of amplitude and phase responses and correlate that to the thickness of the 3D printing. So when we do printing, right? So at the same time, we also identify other co-design challenges. For example, if you just look at these 2 surfaces, right? The left surface is more rough than the right-hand side. Remember, 3D printing is not that accurate, right? So if you have very different values all over the pixels, and you're going to make a lot of printing noise, right? So we identify that a smooth surface of the entire board that you have, you're going to get better correlations to the actual hardware performance. Okay, so that's why later on we also develop a co-design algorithm. So without losing too much of the accuracy, how can we smootherize the entire thing, which is very similar to optimizing for either structural sparsity in conventional neural network, right? So you can see this is getting more smooth, but give you relative same accuracy at the end. So kind of the infrastructure is offering new capabilities for people who are interested in just exploring algorithms level without knowing anything about optics, right? So you can still use our infrastructure to do just algorithmic work. Okay, so at the end, I wanted to just quickly discuss about the engineering efforts. I know there's not a lot of fun thing we can discuss, but this is actually very, very important and costs a lot of time for us during the engineering process of our infrastructure, is how to make this system run fast, right? So we have done a lot of things by configuring the backend to accelerate the 3 kernels, which is 2-dimensional FFT, inverse FFT, and complex matrix multiplication, right? So I know some of you might use complex modules in PyTorch, but at the time when we started this project, PyTorch doesn't even support a complex modulation. So you have to manually develop a kernel that has amplitude computation part, imaginary computation part, and then you build a new one called complex matrix multiplication by yourself. But now they have all our complex modules supported, and we have also switched to that. But at the beginning, we are able to get like almost from like this is from was 3 to 4 days in training back to the time in 2018 and 19 and later on in their Nature Photonics paper. But now we are able to bring this down only to less than 10 minutes. So just to emphasize this part. And so now we have Infra. I just want to show you a few quick advanced case studies. So we bring in the skip connection concept from conventional neural networks that is significantly improving the performance for segmentation, right? So this is I forgot the name of this data set, but it was used to do a segmentation test. And this is the ground truth. What we are getting. So this is the ground truth, right? So we are doing a banner. At this case, we're doing a binary segmentation, but now we are able to do more complicated version. And here is showing the differences between with or without the skip connections in optical domain. How much difference you can get from the result part. And remember, what I want to show is not just about the performance showing in comparison here, but also show how simple it is to explore different neural network topologies in optical neural network, in diffractive optical neural network, right? So all you need to do is to do this, right? So you can see the X3, X4, and to do skip connections is just to add X1 here, right? So in optical setups, you have to do a little bit of routing of the optical signals, but in simulation, you can just it is simply supported by just like a PyTorch, okay? And taking this, we are able to do a little bit of autonomous driving test. So this is what we have done in our lab. We built we bought a map, and so we try to make the car drive on this using optical kernels as the segmentation engine. So one thing I want to emphasize is that we actually train everything is trained on right turn only, and it is able to do left turn in our testing cases. So this is the label. The label is collected by, I mean, this is manual label, right? So one of my students took the videos and labeled these other conventional methods, and then we train. This is the output of the DON. Okay, so you can see we can generate the control with these. It pretty much matches what is on the map. Okay, and then we take this out to the outdoor, and this is more complicated because you have a lot more obstacles and different objectives. But you can see still we are able to identify the road edges, right? So, but things are getting more complicated when you get snow or raining. But this kind of still working in progress. So I think I'm running a little bit out of time. But we just for references, we also work on adversary study, right? So even in light, you have adversaries, but the adversaries is a lot more interesting than just doing digital, because you have you can have invisible adversaries, right? So the images that you see might not have an adversary that is visible to your eye. So it might look exactly identical, but it can still confuse the system, because you can do a face attack, right? So face is not visible to human eyes. So if you're interested, you can take a look at our laser photonic review paper that we have a fully experimental validations on how the light adversaries can be identified using adversary algorithms, and also how that can be engineered on the hardware systems. Okay. So I skip this to the very end. So you can please take a look at our open source infrastructure if you are interested. And the first author of this paper, my student Engneering, is going to deliver the talk in ASPLOS 24. I mean, the paper was in 23, but the talk is in 24. So to quickly summarize, so we are able to address the problem from programming infrastructure, end-to-end core design, and also with a domain-specific algorithm. I think we kind of addressed a little bit, a small piece of the optical system for AI applications. There's still a long way to go, but the concept is from the computer engineering point of view, we are able to connect the physics with the real-world system with a very efficient runtime system to make everything integrated. And at the end, we have some of the advanced case studies, like adversaries study, architecture exploration, like autonomous driving, and we also work on a little bit of material development. So this is a team. So Inje is kind of the leading author of all the works, and she is also interested in a faculty position in the future. And Daniel was the student who worked on this autonomous driving optical system, and he is getting a lot of offers for a PhD study from Princeton, MIT, and Harvard. And Minhan is postdoc who worked on the theories behind, and Professor Vilu Gao from University of Utah and his two students are working on the hardware engineering and device deployment. So, and this is my group, and I think that's it for my talk. Yeah.
Okay, thank you, Cunxi. So this is really very interesting talk, and so I actually have several questions to ask. But first, so any questions from the audience? So you can unmute yourself or input your question in the chat box. I think maybe I can start first.
Sure.
So,
yeah.
Yeah. So, so like in your talk, so some of the example DON is like 3-layer or the 4-layer. So I was wondering, so actually, so it seems that it is a little bit different from the convolution network typically we mentioned in the computer vision, right? Because I don't see kind of the nonlinear activation function there.
Okay, that's a very good question. So I guess you're wondering why with just only 3 layers we are able to learn like a segmentation task, like pretty good, right? So yeah, so it's where does the nonlinearity come from is the question. So I'm going to show you there are 2 pieces of nonlinearity, right? So in optics they define nonlinearity very differently, but if you look at numerically from neural network point of view, the first nonlinearity comes from the sine and cosine here. So theta is the trend parameter, right? So if you think about as just a neural network, right? So you're going to have sine and cosine applied to parameters that is trainable, and this is used as part of the propagation of the entire forward function. So this is the first stage that you're going to have a nonlinearity in your, let's say, neural network modeling. So you can't say, so this is not nonlinearity in diffractive optics. So they treat nonlinearity in optics very differently. But from numerical point of view, this is the first place that nonlinearity is introduced that really makes the gradient propagation more effectively. Okay, there's another set of nonlinearity comes from the output side. So if you're measuring the output of the intensity values, which is a squared plus b squared. Remember, this is at the end of the propagation, right? So you're getting a complex value that represents the light, right? So a is the real and b is the coefficient for the imaginary. So when you do a square and then square root of it, this is another set of nonlinearity that is introduced in the system. So you kind of have nonlinearity if you're thinking about backpropagation or computation graphs. You have that at every single layer and at the output. So that's why the system is actually trained very effective with backpropagation and can handle some very complex examples. So we are currently working on even graph neural network, and it can do graph neural networks as well, like on Cora and some other like social network graph data set. Yeah.
Thank you.
Yeah, this is a very good question. I got this question like every time I give a talk on this.
And any question from the audience?
Hello.
I should have some.
Hi, this is Xiang. Actually, I have a question also on this page.
Okay.
Actually, on page 10.
This one. Okay.
Yeah. Actually, you mentioned this distance z. So what is the Euro size? What is the Euro length of this distance?
Okay, very good question. So I don't know if you worked on different optics in the past or not. Have you do you have experience on that?
No, actually,
No.
I'm just
Okay, yeah. So
interested
then
in
that's fine. So
this paper. Yeah.
sure. Yeah. So numerically, as you can see, Z is basically changing the strength of the diffraction, right? So if you think about diffraction in real world, right? So if you put it close, if you diffract less, if you put it further away, the diffraction strengths get stronger, right? So but it's a trade-off. You can't just if you put it too close and the parameter is not doing anything to the function, right? So you're not learning complex function. You're not able to learn very complex neural network. If you put it too far away, the light is going to diffract like with a very big angle. You're going to lose a lot of energies, right? So what you're capturing is only a small part of it, right? So, yeah, it's a very good question. So this is actually a hyperparameter. If I'm showing you this figure, maybe it's better. So I said this is 11 inches, right? So in this specific system, because our device is just too cheap, each of these is only like $2,000. And the diffraction strength is limited by the pixel size here, the diffracted. So we need to put a little bit further away. That's why the intensity at the end is a little bit small. That's why we put a like small a black box. Otherwise, if you have a more expensive one, like what we have now is like $15,000 per specialized modulator, you can put it very close by because the pixel size is very small and you have a much stronger per pixel diffraction capability. Yeah, very good question. Yeah, so this D has to be tuned. Yeah,
from this photo, it seems that the distance Z is usually like 10 or 20 centimeters, right? Do you think that it's possible to
do integration?
Minimize this distance so that, for example, the optical neural network can be, compact and then make a chip?
Yeah, very interesting question. Very good. Yeah, this is what we are working on right now. So you need to do a very advanced engineering on the device side because this is really for proof of concept that we can use our system to engineer the entire system on very cheap setup, right? But we are currently working on the integrated chip, which is you need much smaller wavelengths, you need more stronger laser, and also at the same time you need very more advanced diffraction unit fabrication, right? And that you can bring down Z to a very small range, and you can do kind of integration on the chip. Yeah, so that's exactly what we're working on now. Yeah.
And also for your layers, hidden layers, so you're using the 3D printers to print them. So is that possible to have be more flexible? For example, like customized or it's flexible to programmable.
Okay, I see. So you're saying about how good is the reconfigurability?
Yes.
Right, of the system. Yeah.
Especially so for the hidden layer. Yeah.
Sure. So for this optic setup, if you use specialized modulator, right? So in this proof concept, you can configure this wherever you want. So this is reconfigurable because you can program the face of each of the pixels. But yeah, if you work on like a 3D printed version, which is something like this terahertz setup, like this one, yeah, it's not reconfigurable. But there are also there are some advanced materials. I think there are some metal material that you can still use to control the phase, even though the original development was you can once it got fabricated by charging up and down. So it's very similar to how specialized modulator works, right? So we are I know a few groups from DOE labs. They're using our frameworks to test like a metal surface in their own optical diffracted system.
I see. Yeah, actually, if the hidden layers can be configurable, then it will be interesting to, because right now you are training the optical neural network and then do the 3D printing, but later on probably you can maybe do some training. I mean, even directly on this hardware, right?
Yes, like that's what we are working on as well. Yeah, so so in this integrated fabrication project, we are also trying to enable on-chip training in this optical system. Yes.
I see. Okay,
Yeah.
thank you.
So yeah, but it's a very, so this project already took me like 4 years. I mean, we're not to make everything happens. I think making a complete chip that is going to, I mean, it's going to take a while. But we recently got a new project, like two grants to support on this. So I think we can probably make, yeah, we're going to have on-chip version.
Yeah.
Hopefully so. Yeah, next
Yeah,
year.
it's very interesting. Yeah, thank you.
Yeah, no worries. So I got another question. Kai Sheng. So with the light decay with more layers, yes. Very good observation. So I haven't talked about that. Let me just show to. Okay, so Bo was asking for 3 layers, right? So why we have 3 layers? So the material in each of these, no matter you use this kind of specialized modulator or the 3D printed version, right? The material itself is going to absorb energies during propagation, right? So let's say if each of the layer absorb a quarter of the energy, it's going to absorb quite a lot because every single layer you propagate is going to be exponential decay, right, in energy consumption. So assume in this system, right, so in our system, we try to have 6 layers. 6 layers is almost like very hard to, it's almost impossible to detect with a very cheap detector. So this camera is only worth like $100. It's just like regular cameras. If you want to do 6 layers or beyond, you probably need a much higher sensitive cameras to do the detection, which costs like maybe 100 times more. And so that's one of the I would say a big limitations like that we have not addressed at this moment is the energy decay in a cascaded system. So if you think about neural network from deep and the wider, right? So in neural network, we try to build deep and wide, like in order to consider the scalability of neural network system. This object system is easier to do spatial expansion, like it's easier to get wider, and it's consuming almost very little cost on that dimension. But on the depths, is definitely harder to do because of this light energy decay during the through the layers. Yeah, very good question. Yeah.
So following that question, so do you need any like the amplifier?
No, we don't do any amplifier because we want to simplify the system. So I want to make the system as simple as possible because eventually we want to target on energy efficiency, right? If you have amplifier itself, it's going to cost a lot more energy than the entire system. So so that's why when we measure things, because we consider everything, right? So I say, you have a system, don't tell me how, I'm not interested how the computing part costs. I'm curious about the entire system, right? So that's the question we want to address or to answer from us. Yeah, like from a system point of view. Yeah.
So in that case, how about the scalability of the model that the device can support?
Yes, as I said, right. So it's harder to get deep, but it's easier to get wide. So we can do a much bigger spatial, like let's say much bigger images, and that costs almost no energy increase in our system. I mean a little bit increase, but so if you so the saying 2 orders, right? In this case for a minute, but if you change this to a HD image like 1080p images or even 2K images we tried, you're going to get like another two orders of magnitude in power efficiency, because it's a spatial increase of the system does not consume a lot of energy because it's all diffraction, right? So per layer, but getting deeper is harder. Yeah, that's for sure. Yeah. I know there's another group. They have so I forgot to include their papers, but from Tsinghua University, and also it's also led by the author of the first author of this very first science paper. They have a new science paper, I think last year. They are able to make this more compacted on the kind of on the chip level, and also using a recurrent version of it. So in that case, they kind of amplify every single time they go to the next layer. But the obvious drawbacks is that they're going to increase the energy consumption quite a lot. So there are different ways to think about the problem. But there's someone already start working on the depth issue of the system.
Thank you. And then any other questions from the audience?
Yeah, if you have any other questions, you can just send me an email offline. If you're interested in this system, we have on our webpage, and we have a code lab version. Like if you code lab on Google, right? So you can just click link, and it will just show a complete example from the beginning all the way to getting the propagation visualized. And you don't need to really install anything on your own system. So Colab works for libraries right now. Yeah.
Okay. Okay, again, so thank our speaker, Professor Cunxi Yu, again, so for this very interesting and very interdisciplinary research talk, and also thank all the audience to join our this week's seminar talk. Okay, see you next time.
Thank you. Yeah.
Thank you, Cunxi.
Bye.
Thank you. Bye. Have a wonderful day.